Okay, now let's start Lecture 5, Propagation through the Atmosphere. Here is the block diagram of the radar, and what we're going to be doing is focusing on the transmission of the transmit signal and the signal back from the target that's reflected off the target as it passes through the propagation medium, which would be the atmosphere. Now, the loss factor in the system losses, there is a loss factor due to the propagation itself. Just the fact that all things being equal, the signal will attenuate in the atmosphere, and that has to be put into play. But also there's another propagation factor, which is the fourth power of the ratio of the actual electric field that's in space to the free space electric field. And we'll see in a couple of minutes what physical effects go into making that F factor different than 1. That's what we'll be studying in this lecture. Now, why do we need to study this? Well, all radars, pretty much, except space-based radars looking at space-based objects, the radars operate in the atmosphere or near the Earth's surface. Ground-based systems, sea-based systems, and airborne systems. Even systems that see into space, that might do tracking of satellites, the beam has to go through the atmosphere. So you can see that the atmosphere has an awful lot to do with the performance of a radar. And you can see just from these examples, we've got atmospheric conditions that can be out in the ocean, and this what looks like a clear day, and here a partly cloudy day. That just brings into focus that atmospheric conditions are going to change with geography, with time, weather conditions. Just if you look at a satellite map of the world, where there are growing hurricanes in the Atlantic Ocean. There might be tropical storms down in the south part of the United States, and it's very dry, say the area of Arizona. There's a lot of different effects with geographic variation. We can divide up pretty well the effect of atmospheric performance into a number of different areas, and we're going to study them one at a time. First is attenuation of the radar beam. And next is the fact that because the atmosphere gets thinner and thinner as you go up, there's going to be a refraction, a bending of the radar beam as it passes through the atmosphere. And that's just because there's less atmosphere at higher altitudes. If you're on climbing K2 or Mount McKinley or Mount Everest, you need oxygen tanks because there's not enough of an atmosphere just 20,000 feet up. So that tailing off of the atmospheric density gives you a bending, a refraction effect, which bends the beam as it passes through the atmosphere. We're going to study that. Next is an effect called multipath, where we have, under many conditions, not all but many, the fact that the beam will go out and it will propagate to the target. And this usually happens when you're pretty close to the Earth. But the side lobes are part of the main lobe. The lower part of the beam can reflect off the Earth in a relatively straightforward manner, specifically if you're, say, over the ocean and it's relatively calm. And the effect is that there will be an interference between that main beam and the reflected beam. And that effect is called multipath, and we'll be studying that. It's an interference effect. And then we have the effect that this is you can think back from diffraction. Say you're in outside of a symphony hall, and there's an open door. The sound waves don't go through the door, but they will go around the door, and you will hear diminished amplitude. You will hear the sound that's going on in that door. Or I'm in one room in my house, and right behind me is the front hall, but there's an open door to my left, and if someone was speaking, the sound waves would bend around, and they diffract. And likewise, the radar beam can diffract over ground obstacles so that you can have non-line of sight propagation. And as I noted earlier, these propagation effects will vary with changing atmospheric conditions and also with wavelength, very much so with wavelength. And also with the time of day, geographical variations, and the like. And we're going to talk at the end about some very distinctly different propagation which happens over the horizon, where the beam actually goes up to the ionosphere and can bend, and you can have propagation of a radar beam or communications beam 5,000 miles away. We'll talk about that in a separate section. Okay, so first let's look at the multiplicity of factors. The atmospheric parameters at a given location vary with altitude. The index of refraction, which is the ratio of the speed of light in the vacuum divided by the speed of light in the medium, or I should say the speed of the electromagnetic wave in vacuum divided by the speed of light in the medium. The rain rate. Certainly if there's a lot of rain, there's going to be a lot of attenuation. The air density and humidity, and the fog and the cloud content in the air. And also the fact that the Earth is curved. The curvature of the Earth it's going to depend on, the surface material on the Earth, because that multipath effect won't take place when you have a very rough surface, like mountains. And it also depends on the sea and land and type of vegetation. So particularly in multipath. But the atmospheric propagation is going to depend on all of these different parameters. Now let's look at reflection from the Earth's surface. This is a trivial view graph. All it just points out is that, you can have here, we have here wave 1 and wave 2 in two different colors. And here, if they're together, and this is the amplitude is a function of time of a sine wave, they can add constructively, or they can add destructively if they're out of phase by pi. And here are the additions. You can see in blue, the addition is twice the amplitude from 0, but that's actually, the voltage can range from 0 to 2 times the single wave, and the power is proportional to the voltage squared, or 4 times the power. But the interference operates on both inbound and outbound trips, so you can have a factor of 16 times the power if an interference effect can make a big difference in the output that's received at the radar. Now let's look at propagation over first a plane Earth, because that's easy to do geometrically and calculationally from a calculation point of view. And then we'll look at it over a curved Earth, which is more complicated. But we'll just go through this in a straightforward manner to give you the ideas. We have a radar and a target, and in blue is the direct path, and in red would be that multipath ray that I spoke about. So the reflection off the Earth's surface, and typically from a target that's close to the Earth, and the radar, of course, in this case would be close to the Earth, you can have interference of the direct signal and what we call the multipath ray. And the total propagation effect is expressed by a propagation factor, that f to the 4th power. The surface reflection here at the surface determines the relative signal amplitudes, this gamma. And it's going to depend on how smooth the surface is, whether it's rough, and the polarization and the frequency. It's very close to 1 for the ocean, and it's close to 0 for rough land. And there's going to be a phase shift that's determined by the path length difference between the direct and the multipath ray. And this will depend on height of the objects and the range to the objects, and also the frequency of the radiation. Now here's the algebra that shows you how we get this factor f. Here we have r1, which is the distance between the radar and the target, which is just the square root of r squared, the distance to them, plus the difference in heights, quantity squared. If they were located at the same height, this would cancel out and r1 would be r. But the aircraft could be higher, it could be lower, and that would change this quantity r1. With r2, we have, projecting down here, we have the height of the radar adding to the height of the transmitter. Okay? Now the phase difference between the direct ray and the multipath ray is just 2 pi over lambda times the difference in the two paths, the direct path and the multipath. And that's approximately 4 pi times the height of the radar times the height of the target divided by lambda over r. We'll show you in a minute the details of that. Here's the direct, and when we look at what we see here, the propagation factor for just is 1 plus the magnitude of the reflected wave plus the phase factor. And I want to note that there's a change of phase of pi at the surface when there's a reflection here. So there's a -1 factor that comes into play. So the two-way propagation factor would be f to the 4th, this quantity to the 4th power. Okay? And now looking at the difference of those two, the reflected path minus the direct path, we get, for the conditions where gamma is approximately -1 and r is much greater than the height of the radar, the range to the target and the radar are much greater than the height of either of them, and the height of the target is much greater than the height of the radar. And for small theta, we get these expressions. And the reflected path minus the direct path is this expression. So the phase difference due to the path length difference is just 2 pi over lambda, 2 h sub r, and the height of the target divided by r. And the total phase difference is that factor, plus the factor of pi, which I mentioned, which is the factor of -1 at the surface. Okay. Now the sum of the two signals, each of unit amplitude, but with phase difference, with this phase difference, is this. Just doing trigonometry. The one-way power ratio is this. Just doing trigonometry, 1 minus cosine theta is 2 sine squared of 2 theta. And a two-way power ratio, that's the one-way power ratio, and the two-way becomes that quantity squared. And now we can look at this one-way power ratio, and we'll get maxima when this quantity is 2n plus 1 times pi over 2, and minima when it's equal to pi times an integer. So what that's saying is that we're going to get a set of minima and maxima for propagation over the plane Earth. And these are the conditions when the maxima will occur, and these are the conditions when the minima will occur. Now, this is what this multipath effect looks like in terms of the target altitude plotted against target range for 3 different coefficients of reflection. Now, when you have a perfectly smooth ocean, say, the reflection coefficient is going to be -1, and that's in black, so you get a very strong lobing effect. If there was some roughness, but not too much, you get a minus, say, 0.3, and you get some lobing. When you have a very rough surface on the ground, say rocks, or something that's absorptive to the radar radiation, you'll get 0, and this will be the target. They'll just be set by the radar equation. So the multipath structure causes our elevation coverage to be broken up into a lobe structure. And the target, located at the maxima of a lobe, can be detected away as twice the free space propagation distance. Notice that. You can see it at twice the free space, but you've got these nulls here, which can inhibit. At other angles, the detection range will be less than free space, and you can get a null echo signal received. And here's the first maxima showing up. That follows from the equations in the previous view graph. Now, this shows the frequency dependence of the same view graphs when I take, if I do this calculation with frequency 1, and then do it with twice frequency 1, you can see that there are a lot more lobes, and they're thinner when you have higher frequencies. So lobing density increases with increasing radar frequency. Okay, here we see some little visuals showing you the one lobe over distance x, and here you get 2 lobes over that same distance. Okay. Now we go to a round Earth. Around Earth calculations are really the same physics, but a little different geometry. The propagation is more calculated, and computer programs exist to perform this transforward, but it's a relatively tedious task. The algebra is worked out in detail in a book by Blake on the radar equation. As with a flat Earth, with a round Earth, the lobing structure will occur also. And here's an example to show you how, as a function of grazing angle, the reflection coefficient can change with polarization, and it can be complex, and it's a complicated entity. So if we have horizontally polarized radiation, and we have seawater, complex dielectric constant of seawater is given by this factor. Okay? The conductivity, of course, is there, and the grazing angle is alpha, and the wavelength. So if you have very low grazing angle and you're horizontally polarized, you're going to get a reflection coefficient very close to 1, and you're going to have that factor pi thrown in, so you'll have a lot of multipath. Over here on dry land, where you have a much lower real part of the a dielectric constant and a very small imaginary part, notice these imaginary parts depend on wavelength, the polarization drops down pretty quickly with horizontal polarization, and notice how it drops off very, very much with vertical polarization. And these are the equations which come out just of solving the boundary conditions for the reflection coefficient as a function of grazing angle, a complex dielectric constant, and yeah, just the grazing angle in trigonometry. Now, to show you what this would look like for a real radar, here we see an SPS-49 shipborne surveillance radar on the USS Abraham Lincoln, and it does air search for this particular carrier, looking for aircraft. It has 13 kilowatts of average power. It's in the lower end of L-band, and it rotates 6 revolutions per minute, and it can see a 1 meter squared target, And we're going to do this calculation with an antenna height 75 feet above sea level with a sea state 3. And this calculation was done by Gregers Hansen, and it's been adapted and re-rendered from Merrill Skolnick's book, our textbook. And this is what the instrumented range of that radar is. It should see that target 1 meter squared out to 260 nautical miles. And this is as a function of height and slant range. And you notice that there are significant lobes where you can see beyond the instrumented maximum range if there was no multipath. And there are places where there are clear nulls. And as we get to higher elevation angles, remember from the previous view graph, the effect drops off. Okay, now let's look at atmospheric refraction.